Okay, so we are going to get into try to lay the groundwork today for factoring all polynomials. Okay, and so through this section, probably take a day and a half, 2 days maybe. We're going to do long division and synthetic division. And those are two algorithms for finding factors that we're going to familiarize ourselves with. Now, the synthetic division one is actually easier, but with that you lose some context. So we're going to start with the long division of polynomials, which is something you guys know how to do if you know how to do long division of whole numbers. Okay. So this section will be an algebraic study of polynomials. Most of the work will incorporate the need to factor. When factoring, we're identifying or synthesizing the objects that multiply to generate the polynomial. So here's my question. If I have 12 as a product and one factor is 3, how do you go about finding the other one? Huh? 12 is my product. 12 is my product. 3 is a factor. How do I find the other factor? What times 3 gives me 12? 4. How did you know that? 12 divided by 3 is 4. So when you're factoring, you're effectively doing division. Yes? Okay. So when we talk about factoring, that's all we're doing. So that's where this long division comes into play. Okay. Now, just some terminology that we've known maybe since the 3rd grade, or we were introduced to it in the 3rd grade, and then we learned the process, and we maybe have forgotten the terminology. But the terminology is important for polynomial division. So when I take a number, so the question is, what's 38 divided by 7? Okay. First of all, I need you to understand 38 is not what we refer to as being divisible by 7. When I say something is divisible by a number, that means the quotient is a whole number with a remainder of 0. Does that make sense? Okay. Now, you can divide any number by any number, yes? Okay. So I could take any polynomial and divide it by any polynomial. Does that mean that every polynomial is divisible by any polynomial? No, because it's dependent on the remainder. Okay. But I could take 38 divided by 7. When I take 38 divided by 7, 38 is called my dividend. And 7 is the divisor, right? Okay. Then I get, when I look at my answer, 5 is my quotient. 3 would have been my remainder. Okay. And we write our remainder over our divisor, so that's where we get our 3/7. So 5 and 3/7 is the same thing as 38/7. Okay. So that's one way that we might have learned it. But this is probably the actual structure that you went through the algorithm with. Okay. So a lot of times you're asked, how many times does 7 go into 38, right? And you answer that with a 5. And you put your 35 down here. You take 5 times 7 gives you 35. And then you subtracted, right? Gave a 3. And then you say, okay, how many times does 7 go into 3? And that told you when to stop the algorithm. That told you, well, 7 doesn't go into 3. 3 is smaller than 7. So when your remaining row is smaller than your divisor, you stop, and that remaining row becomes your remainder. Okay? And we put R3, right? Does that make sense? You remember doing that? Okay. Still got our quotient, still got our remainder, still got a divisor, still got a dividend. And then those locations specified up there. Now, there are algorithms. An algorithm is simply a procedure that basically a lot of algorithms are like yes, no, like statements, or the answers to the procedures are yes or no. And if it's a yes, you continue on with the algorithm. It keeps operating until you get to the no. So this basically, this algorithm of division is, does 7 go into 38? Yes or no? Yes, it does. So you divide, how many times does it go? Okay, 5. Okay, and then you continue the algorithm. The next step says, okay, now you take your 5, you multiply by your divisor, and you get this 35. And you go 38 minus 35. That's another step of your algorithm. You get 3. And now the question is, does 7 go into 3? The answer is no in this case, right? So because we answer no, it stops the algorithm, and you've got your final result in your remainder. Okay. If it was yes, you would keep going through the division. Okay. So algorithms are things that usually are kind of repetitive, and have a yes or no response, and yeses keep that algorithm driving, no's say stop. Okay. So when we talk about a division algorithm here, it's basically going to be a procedure that structures polynomial division for us, okay, and how we can ultimately factor any polynomial that we ever come across. Okay, it says if p of x and d of x are polynomials, so you got two polynomials that you're going to divide. Okay, it says d of x cannot be 0 because we're going to divide. Okay, so the denominator can't be 0. So then there exist unique polynomials q, r, or q and r, where r is your remainder, q stands for your quotient. Does that make sense? Okay. Now, the algorithm says you continue to find parts of q, essentially, parts of your quotient, until r is either a 0, numerical value of 0, or it's a degree less than the degree of d of x, which that basically right there tells you how and when to stop your division. Okay? It's like up here, we stop our division when that number right there becomes less than the divisor, right? Does that make sense? And that's what they're basically telling us in this algorithm, is that you're going to stop doing division when you get a row here like that, that is 1 degree less than your divisor. So when we see that for the first time, we'll talk about this again. But they're basically telling you that you can take a polynomial divided by a polynomial, and that should be equal to some unique quotient, which is a polynomial, plus a remainder divided by your divisor, and that remainder is a polynomial. Okay? Now think about this. If this was 38 and this was 7, 38 and 7, this would have been 5, and this would have been 3, and this would have been 7. Does that make sense? Okay. Now, here's my question to you. If I take 5 plus 3/7, okay, because that is essentially like p divided by d. It's this side here. If I multiply by my divisor, so looking at this, what was my divisor by looking at that right there? The 7, right? 7 was my divisor. If I multiply everything by 7, what's 5 times 7? 35. What's 3/7 times 7? 3. What's 35 plus 3? 38, which was my original polynomial, right? Does that kind of make sense? Okay. That's exactly what this thing over here, when it says or, okay, that's exactly what this is stating here. If I want to solve this for p of x, how do I do that? If I multiply this by d of x, does that cancel and that cancel, leaving me p of x? So if I multiply this side by d of x, is it q of x times d of x? If I multiply the right-hand side by d of x, do those cancel again, leaving me just r of x? Does that make sense to everybody? So these two things, these two structures are identical. They're the same thing. One is just solved for p of x over d of x, and one of them is solved for p of x. Okay? And we're going to be asked to bounce back and forth between both of them. Okay? So as we go through our examples, we'll obviously see that. All right, so again, I think it's important to see this structure, but then to practice this, obviously it makes sense to actually go through some specific examples. Okay, so let's go to the next one, and we'll do an example. So we've got the idea that we're going to take 6x squared minus 26x plus 12, and we're going to divide it by x minus 4. Okay? It says express the result in each of the two forms of the division algorithm. So they want us to figure out what does p of x divided by d of x look like. Well, p of x is the polynomial that we are dividing. So we're dividing 6x squared minus 26x plus 12, and x minus 4 is the polynomial that we're dividing by, right? That's our divisor. So x minus 4 will look like that, okay? So that's originally what they're referring to when they say divide 6x squared minus 26x plus 12 by x minus 4. In WebAssign, you might see a question that is the beginning. They'll just say divide, and they'll give you that. Okay, they won't give you the sentence or anything like that. Or they might say simplify or write using the division algorithm. Write the alternative version of this. Okay. So what that means to us, a lot of times we take 38 divided by 7, and that's essentially what we're seeing right there, polynomial divided by polynomial. But when things get more complex, we don't write it this way. We don't actually run through the algorithm this way. We run through the algorithm that way, don't we? So that's how I'm going to transform this into 6x squared minus 26x plus 12. And then we'll put x minus 4 out here. Okay, so the way you guys have done this before. Okay, this is an Algebra 2 concept. And the way you were introduced to it last year, and it's the way I'm going to, because it's the way I was taught, it's the way I learned how to teach it this way, is that I am going to ask the question, what can I put here so that when I multiply by x, it gives me 6x squared? 6x. Now, why do I ask it that way? Because a lot of times, if I'm going back up to the 38 divided by 7, the question is, how many times does 7 go into 38, right? Okay. How many times does 7 go into 38? So in order to do that, we have to know a number that is pretty close to 38 that 7 is a factor for, don't we? What is that number? 35. So instead of asking how many times does 7 go into 38, I always ask myself, or I think it's important to be able to see this or recognize this, what number less than 38, what is the first number less than 38 that I can make 7 go to or grow to through multiplication? And that number is 35, right? And then I ask myself, okay, well, what do I need to multiply 7 by to get 35? And it tells me 5 times 7 will give me that 35, right? So with long division of polynomials, that same question, what do I need to multiply x by to get either equal to or something less than 6x squared? And we can always get equal to it. Does that make sense? Okay, so 6x is that answer. Now, another thing that you can do is you can ask yourself, if I take that right there and divide it by that right there, what is that quotient? What's 6x squared divided by x? 6x is what goes on the top of that division bar. Okay? So okay with everyone? So now, just like the division algorithm back in 3rd grade, you take the 5 and you multiply it by the divisor, right? So now I'm going to take the 6x and multiply it by my divisor. Now, the only thing you got to be cautious of here is your divisor is a binomial, right? So what's 6x times x? 6x squared. And what's 6x times negative 4? Negative 24x. Okay. So now, up here where it's 38 and 35, what do we do to get that remainder then? You subtract, right? Okay. Now, I don't like subtracting because, and it's not, but 6x squared minus 6x squared, that's easy. But negative 26x minus negative 24x, I got to sit and think, I got to maybe say that to myself a couple different times to remind myself that I'm actually adding there, right? So what I like to do, what is the same thing as subtracting? Adding the opposite. So I'm going to actually put a plus sign out here and then make all of these terms inside the opposite. You can do it however you want. Okay, if you want to subtract, straight up subtract, go ahead and do it. But I like to add the opposite, and that's how I'm going to do it in class. Okay. So now if I add down, if we've done this correctly, those terms should disappear. It gives you 0x squared. So it's just 0. Negative 26x plus 24x is negative 2x. Okay. Now, much like when so let's say that we just left this as a remainder of 3. But if you guys remember like long division, let's say we wanted like 381 divided by 7. What do I do with that 1 now in this second portion or second step of this algorithm? You would drop it down there, and now you would ask the question, how many times does 7 go into 31, right? And because this number is greater than that number, you can continue with the algorithm. You can continue the division until that number there becomes smaller than that. So right now, This plus 12 needs to be dropped down because that's analogous to that 1 right there. So I bring that 12 down. And now the question is, can I keep doing the division? And the answer is yes, because there is still a whole number quotient that you can multiply, or a whole number value that you can multiply x by to get negative 2x. And then the reason we can continue with the process is because this here, that exponent, is either equal to or greater than that exponent. And that's what drives the kind of the iterations of the algorithm. How many times I can keep going until this one here is less than that one. So what can I then multiply x by to get negative 2x? Negative 2, okay? Or you could have thought about it as, what do I need to, if I take that term right there and I divide it by that one, negative 2x to the first divided by x gives me negative 2, right? Okay? So now I'm going to take my negative 2 and multiply it by my divisor. So it gives me negative 2x and then plus 8, right? I'm going to change the signs. I'm going to add straight down. So it's going to give me 0, and that's going to give me 4, right? Now, here's my question. And you don't have to write this, but this would be x to the what? X to the 0. Do you see how that exponent is less than that exponent? Which tells me that x minus 4 will not divide 4 a whole amount, right? Does that make sense? Okay, so that becomes my remainder, and I stop the algorithm. Okay, so I'm just going to write remainder here. I put r and then 4. Okay, now they ask us to write this a couple different ways. Okay, so we started off with that thing there, okay, which our algorithm above in that blue box that we talked about said P of x over D of x should be the same thing as the quotient plus the remainder divided by the divisor. Okay, so the quotient in this case, 6x minus 2. Plus the remainder divided by the divisor. So that is one way of writing P of x divided by D of x. Okay? Now, they may ask us to write it as just P of x. Okay? Well, that means, so right now, this is kind of move some stuff around here. That's what we just determined. This here is the same thing as that structure there. Does that make sense to everybody? Okay. Now, if you multiplied both sides by x minus 4, would you get P of x times D of x times Q of x plus R of x? Okay, multiply both sides by x minus 4. So that on the left-hand side would just leave you 6x squared minus 26x plus 12, right? On the right-hand side, that needs to be multiplied by x minus 4. And this needs to be multiplied by x minus 4. So if that's multiplied by x minus 4, what happens to that denominator? Cancels out, and you're just left with plus 4, right? Okay. So right now we have this to be true, along with this to be true. Okay, and they're going to ask us to be able to do both. But that yellow one ultimately ends up being the best one, because think about this. Now, obviously, it's not the case here in this situation, but what if that 4 was a 0? What if that 4 went away? You would then have a polynomial down in factors. Does that make sense? Okay, so that's what our hope is that when we get a remainder of 0, that we're left with then a series of factors that generate our original polynomial. Okay, So that means that instead of x minus 4 being the divisor, we would have to know a divisor that would generate that 0. And we've got some tools that are going to allow us to do that in the next couple days. Okay? Let's take just Desmos real quick. I think I've got it plugged in already. So this is P of x divided by D of x. And then this is Q of x plus my remainder over D of x. Okay? And just to show, so it's what I've got highlighted there in blue, just to show that they are equivalent, choose an x value. What can x not be? X cannot be 4, right? Because I can't divide by 0. If I put 4 in there, it's undefined for both of them, right? So that would not be enough to give me information whether these are equal or not. So let's choose a different number. Let's just choose 1. Okay, so they are the same, right? Okay, so I've been able to take this and alter it into a new format. Okay, now maybe 1 was just happenstance. Maybe it was a coincidence that these two things were unequal for all numbers except for 1, and I randomly chose 1. Okay, so maybe that's not enough proof. So maybe I try 2, or add 2, so I get 12. But they both turn out to be 70.5, right? If I'm trying to see if two things are equal like this, I can choose numbers like 1 and 2 and 3 and stuff like that, but there might be a coincidence sometimes that they're equal at those spots. Okay, so what would you do? Why did you choose 74? Big number, random, right? I'm going to exaggerate that a little bit. Would you agree that that's pretty random? That there is no way on Earth, statistically speaking, that if those two things were unequal everywhere else except for one spot, that would be the one spot that they are equal? That would be very rare, correct? Okay. So if I'm uncertain about whether things are equal, formats are equal, and I want to check them, I usually don't just do, they equal, they're the same thing at 2. I try to choose a number that is pretty rare for it to be a coincidence that they're equal there. Does that make sense? You can do it that way. Okay. So another thing, so then if that's the case, let's take this one. So we said 6x squared minus 26x plus 12. That's my original polynomial. Is that the same thing then as 6x minus 2 times, what was it, 6x, oh, sorry, yeah, it was x minus 4, sorry, x minus 4, and then plus 4. So those are the same thing, right? Okay. So that is the division algorithm, okay? So that is, again, the basis for all factoring that we currently know how to do. Okay, so this will work with, factoring like x squared plus 5x plus 6. If I know one of those factors is x plus 2, then I can go through long division and get the other factor to be x plus 3. Okay, but we have shortcuts that work faster than this. But this is kind of the governing tool that allows those shortcuts to work. If I want to divide 2x cubed minus 7x squared plus 5 by x minus 3. This one's a unique question because there's an added step here, or an added procedure that we need to be aware of. It's not 100% necessary. Yeah, but if you neglect it, a lot of times people that neglect this mess up. Okay, so what do you tell me there's not here? There's not an x to the first. So when I do the long division, yes. So I have 2x cubed minus 7x squared. Now because there's no 0x to the first, or sorry, there's no x to the first, that means it is a 0 times x to the first. So we put that in as a placeholder. And you have to do that as many times as you deemed necessary for the terms that are missing over here. Okay, so if I would just had like 2x cubed plus 5, then I would have had to have a 0x squared plus a 0x. Does that make sense? Okay, so when we're doing the long division, we put things in descending order. Okay, if I have something x to the 7th as my leading term, then I need something x to the 6th, to the 5th, to the 4th, to the 3rd, to the 2nd, to the 1st, and a 0. Okay, I need all those terms written in. And basically what it does is it aligns things for us in our procedure here. And we'll talk about it when we get to that stage in the division. But that is an important thing to do. Like I said, it's not 100% necessary, but if you don't put it in there, a lot of people, in my experience, have struggled on this concept because of its lack of inclusion. So what should I put here to get the ball rolling here? What do I multiply x by to get 2x cubed? 2x squared. Okay, and again, remember, that is the same thing as taking 2x cubed divided by x and getting that result. Okay, so if you're a person that prefers to do that division. So now I'm going to multiply 2x squared times x is 2x cubed. 2x squared times negative 3 is negative 6x squared. Good. So now I'm going to multiply by a negative and then add straight down. So those disappear, and you're now left with negative x squared. Okay. Now I'm going to drop down the 0x. Okay. So let me kind of make a comparison here to, because somebody asked this in the last class, and I think it's a pretty important question. Let's say I want to divide 3,871 by 7. Well, we already said that 38, that needs to be a 5, right? So I go 35. Okay. I'm going to subtract, so it gives me a 3. Now, what did you guys learn to bring down here? The next, did you bring down all of them? Did you bring that? So you haven't used 7 and you haven't used 1. Did you bring them all down? You guys just brought, you're taught just to bring the next one down? Okay, so that works. That's fine, because all you're going to do, whether I bring it as 337 or 371, all you're going to do is see how many times does 7 go into these two first ones, right? Okay. So again, that would be 5, right? So then I have 35 and bring my 2 down. And now I got to go all the way back up here and drag my 1 down, right? Okay. In long division, that gets kind of messy. Okay, going all the way back up to the beginning. Thank you. Going all the way back up to the beginning and bringing down the things that you haven't used. There is absolutely nothing wrong with bringing that 1 down here and saying, okay, 35 gives me a 2 here. Now bring that 1 down there. Does that make sense? So I'm always going to bring down everything that I haven't used from up here. Especially with, like when we start doing these, you can even see that the one that we've already done. My work starts to get skewed one direction, and I don't line things up very well. Okay? And I know that. I know that's the way I write, so to address potential issues that I've come in contact with in the past, I just bring it all down at once. Is that okay? Okay. So now I ask myself, what do I multiply x by to get negative x squared? Negative x. So then negative x times x gives me negative x squared. And now here is the purpose for having this placeholder. Now negative x times negative 3 gives me positive 3x. Do you see how that placeholder, if it was not there, that placeholder would be, the 5 would be in its place, right? That 5 would be right there, and now you would have like negative x squared plus 5, and you would have a 5 and a 3x stacked on one another, and that confuses people. There's nothing wrong with it. You just got to realize they're not like terms, okay? And that you can't add them like that. But a lot of times when people do that, they'll put like the 5 here and then the 3x, and they'll say, oh, that's 8x, okay? The placeholder is going to eliminate the stacking of unlike terms, okay? So now I'm going to change signs and add straight down. So those go away. You're left with negative 3x, and we're going to add 5. Okay, and bring that 5 down. What should go next in my, so negative 3. So negative 3 times x gives me negative 3x. Negative 3 times negative 3 gives me a positive 9. I'll negate things and add straight down. So it gives me a remainder of negative 4. Okay. When we write this then, so we've got our p of x over d of x format. If you remember, that's the quotient, which was 2x squared minus x minus 3, plus then the remainder, then divided by the quotient, x minus 3. If I want to write it as just p of x, then it is going to be 2x squared minus x minus 3, my quotient, times my divisor, plus then my remainder. My remainder in this case is negative 4. So those are alternative ways of writing the exact same information. Is that okay with everybody? And the hope is, so that top one, we got p of x over dx. That's beneficial. That's nice. It's great. But this is where the next couple sections are going to target. Because again, this identifies an alternative way of writing p of x, right? So if I have an alternative way of writing p of x, and the hope is that it's just a product of binomials and trinomials, then that is effectively a way of factoring. Okay. What is nice is eventually, so when we start doing, obviously this is going to be, the purpose of this right now is to factor all polynomials. The next chapter we'll talk about rational functions. Okay, and if you guys remember rational functions, they have asymptotes. Okay, the remainder tells us something very important about asymptotes of some rational functions. Okay, it actually ends up being the equation for asymptotes. Okay, so this procedure has a lot of uses down the road. It has procedures and a lot of branches of mathematics later on as well. Okay, but we have found that writing all that stuff out gets messy. We don't necessarily like all the variables and all that kind of stuff being used. So we've created a technique called synthetic division. Remember that phrasing? Okay. It is identical to long division. Okay. It is the exact same thing, but we eliminate the use of the variables. Okay. When you do that, things get a little cryptic looking. They get a little bit. You gain efficiency and you gain, I think, clarity in your work, but you lose context. Okay. Which can confuse people. So tomorrow we'll take this long division and we'll transfer into synthetic division. And once we revisit that idea. Synthetic division can only also be used with dividing, our divisor being a first-degree polynomial. So the long division, you can divide anything. Okay, if I want my divisor to be a quadratic or a cubic or something like that, I can do long division with it. Synthetic division limits me to only being able to do division with linear terms. Okay, but like I said, it makes the work a little bit cleaner looking. And you can be a little bit more efficient with it, but at the same time, you lose, I think, a little bit of understanding based on the structure. But that's where we're going tomorrow. And then those two procedures will allow us to make a connection along with the zero remainder theorem to make the argument of how to factor any polynomial you ever come across. Okay? All right. No new homework yet.